Welcome in Carudar. Today we are going to learn a very important experiment to study the path of ray through a triangular prism and measuring its refractive index of the prism material. Let's start. Here, as you see here, we have the triangular glass prism and we have here this, here this experiment to determine the ray path through a glass prism. What do you need? What are the tools that you needed for this experiment? We need, of course, equilateral triangular prism, and its refractive angle of the prism A equals 60 degrees. We need pins, we need a protractor, we need a ruler. What's about the procedure? What's about the steps? What are you going on? Place the glass prism, as you see here, on a sheet of drawing paper in a vertical position and mark its base and mark its position with a fine pencil line. That's for the first step. The second step, place two pins such that one of them, A, is very close to one side and the other, B, is about 10 centimeters from the first one. As you see here in this figure, here we stick two pins, we fix two pins and the other side, and we make the extension here and the extensions here, and we make a line joining between the two pins and the other two line joining and another line joining the two pins, the other two pins, and we finally obtain this figure. So from this figure we can calculate phi 1, theta 1, yes, phi 2, theta 2, and change every time, So by this activity we can calculate the angle of deviation and we can calculate the refractive index of the prism. After that, from this figure, from the previous figure, we can conclude that the refractive index N depends on the wavelength. So, for example, the red light has a long wavelength, but when the wavelength increases, what will happen to the refractive index and the angle of deviation? Yes, the refractive index is very small and the angle of deviation also is very small. So there is a relation between the wavelength and, on the other side, yes, refractive index and the angle of deviation. If you have a high wavelength, so you have a small or a low refractive index, a low or small angle of deviation. So the refractive index N depends on, yes, the wavelength lambda. Then the minimum angle of deviation depends also on the wavelength. Thus, if a beam of white light falls on a prism set on the minimum angle of deviation, the emerging light disperses into 7 spectral colors: red, orange, yellow, green, blue, indigo, and violet. These 7 spectrum colors. It's concluded that the red light has the least angle of deviation, but the violet light has the maximum angle of deviation. This is related to the wavelength. Okay. So the visible spectrum colors into which the white light is dispersed, is splitted, and can be arranged, yes, as I told you before: red, orange, yellow, green, blue, indigo, and violet. So we have here this triangular prism, yes, here white light, and it disperses, as you see, in these colors. So when I ask you to give reasons for the prism disperses white light to its 7 colors, because the wavelength of each color is different from the other. So when the wavelength of each color is different from the other, so the refractive index depends on the wavelength. Also, the angle of deviation depends on the wavelength. So yes, we have here 7 spectrum colors. We have here 7 spectrum colors, as you see. Okay, after that, when I ask you to give reasons, the rectangular glass block doesn't disperse white light to its 7 colors. The rectangular glass block, it can be considered as, yes, 2 equal and opposite prisms. The first prism disperses the white light into 7 colors, but the second prism cancels the dispersion, cancels this dispersion, so it emerges as a white light again, So the rectangular glass block doesn't disperse white lights into 7 spectrum colors. Why? Because the rectangular glass block is considered as 2 equal opposite prisms. Okay, from the same material, the dispersion of the first one is cancelled by the second prism. Okay, that's for this question. Another question. The red color has a minimum deviation, while the violet light has maximum deviation in a prism. Why? It is related to the what? Yes, wavelength. High wavelength, small refractive index, small angle of deviation. Small wavelength, high refractive index, high angle of deviation. Please don't forget it. So the red color has a minimum deviation, the violet light has maximum deviation, because the red light has maximum wavelength, so it has minimum deviation, while the violet light has minimum wavelength and the maximum deviation. Let's move to another topic, which is the thin prism here. What's meant by the thin prism? The thin prism is a triangular glass prism, but it has only one difference, which is, yes, it has very small angles, the small refractive angle of the prism. It is a thin prism. The thin prism is a triangular glass prism, but its angles is very small. Its apex angle is a few degrees, not exceeds 10 degrees, maximum, not exceeds. So a few degrees, and it is a position of minimum deviation. So the thin prism needs 2 conditions, which are, yes, first one, few degrees, the apex angle doesn't exceed 10 degrees. The second condition, this thin prism, is located at the position of minimum deviation. So from the relation n equals the relation of the position of minimum deviation, n equals sine alpha naught plus a over 2 divided sine a over 2. In the position of minimum deviation, sine this angle equals this angle. Sine this angle equals this angle. It means sine alpha naught plus a over 2 equals alpha naught plus a over 2. Sine a over 2 means equals, yes, a over 2. Here, yes, they are small angles, but in radians, of course. So sine, but it is approximately, not exactly, it is approximately. So sine alpha naught plus a over 2 approximately equals alpha naught plus a over 2. Also, sine a over 2 is approximately equals a over 2. So from these 2 equations, we can substitute them in the main equation, which is this, yes. So here, n equals alpha naught plus a over 2 divided a over 2. So we can cancel 2 with 2. So it will be, yeah, n equals alpha naught plus a over a. So we can make cross multiplication. So alpha naught plus a equals n times a. After that, we can move a to the other side. So here, alpha naught, or make a substitution for alpha naught only. Alpha naught equals, yes, na minus a. Na minus a. Alpha naught, again please concentrate very well. N here equals alpha naught plus a over a. So when we make cross multiplication, so alpha naught plus a equals n times a. Okay, that's clear. Okay, so alpha naught only, alpha node only equals Na minus A. After that, we take A as a common factor. So alpha node equals A as a common factor N minus 1. This is a relation. It can be used for calculating the angle of minimum deviation, but in the case of the thin prism. In the case of the thin prism, but in a case this prism is placed in air. This prism is placed in air. If this prism is placed in a liquid, so it will be here N prism divided N liquid. N prism divided N liquid. Okay. After that, so what's the application of the thin prism? The application of the thin prism is the same application for, yes, for what? For the application of the triangular prism, which is, yes, deviation, and dispersion of white light. So the thin prism, it is used in deviation and dispersion of white light. Deviation and dispersion of white light. That is the application of the thin prism. Okay. We have here example for the thin prism. It is very important. A thin prism of refractive index, 1.5 is placed, yes, in a liquid of refractive index 1.2. Has angle of deviation 2 degrees only. Find the angle of the prism from the relation alpha node equals A, open between the brackets, N minus 1. But here N liquid to glass. From, yes, so here N glass divided N liquid. N glass divided N liquid. N prism divided N liquid. So alpha node equals 2. A, we don't know it. We want to calculate it. N glass is 1.5. N liquid 1.2. Minus 1, minus 1. So from this relation we can calculate A as, yes, A equals 8 degrees. A equals 8 degrees. At the end, I hope to understood our points for today. To understood the experiment, the thin prism, and the examples for it. Thank you and hope to join us in the next part.